All right, today we're going to talk about polar coordinates. And we have, for our entire map life, talked about rectangular coordinates. Okay, so let's review what we know. So we're gonna recall the things that we know here already. Okay, so let's recall the coordinate system that we're all used to, the one that we all know and love. All right, where this is x and this is y, and we call this the rectangular or Cartesian plane. All right. And this point we affectionately know that is 0, 0 here is the origin. And if we were to try to find a place in space on this rectangular or Cartesian plane, what would we do? Well, it's like we're giving directions to somebody. We would say we're going to go east this far and we're going to go north this far. Or we'd say we're going to go west this far and then south this far, which would put us in quadrant 3. But I'm going to, for discussion purposes, put us in quadrant 1. Okay, and so we have a point in space called xy. Now, how did we get to xy? Well, we marched over x in the horizontal direction and we went up y in the vertical direction, and it got us to this point in space. And we could describe any point in space in this rectangular or Cartesian plane by an ordered pair xy coordinate. Okay, so that's what we're familiar with. But there's another universe called a polar plane here. So what I'm going to do is I'm going to draw something that we call the polar axis. And in polar coordinates, we only have the horizontal polar axis. We do not have a vertical axis. So I call that the axis that shall not be named. So I'm going to put that on here lightly, because that gives everybody kind of a frame of reference. Okay, so this is the polar axis. It's a horizontal. And this point right here now is no longer called the origin, but it's called the pole. Okay, and if I wanted to label a point in space, and we'll put it in the first quadrant here, instead of giving directions saying that I'm going to go east so far and then north so far, I could say go in this direction. So I could say go northeast 5 miles. Okay, so that means go out radially 5 miles. And I could do that and be in any point in space in this plane. And we're going to call this the polar plane. So the ordered pair here is, instead of xy, it's going to be r comma theta, where r is this distance from the pole to your point, and theta is how far you rotate it. Okay, so if I was going to plot a point, I'd go out radially and rotate, even though I would walk this direction. Okay, so let's have some formal definitions here for some of the variables that we have here. So r, these are going to be polar coordinates. R. Well, what is r? R is the directed distance from the pole. And theta, by definition, is the directed angle measured from the polar axis. Okay, now, just like we were doing in trig, if you rotate counterclockwise, and that's my abbreviation for counterclockwise. Counterclockwise means I'm going this direction. So I'm going to put this direction. If you rotate this direction, your angle is theta is greater than 0 or positive. If you rotate clockwise, which means you're going this direction, theta is less than 0. It's negative. Okay, so those things are still familiar to us. Okay, so instead of talking in XY coordinates, we're going to talk in R theta coordinates, all right? All right, so let's see what that means. So what we're going to do is we're going to plot some points. Now, what I have here is a polar graph, and we need to talk about that for a minute, a polar graph. Now, we're used to, in trig, having angles that were in the standard angles were pi over 6, pi over 4, pi over 3, pi over 2, all of this. Now, I want you to notice that between 0 here, I'm going to call this 0, and this here, pi over 2, I have 1, 2, 3, 4, 5, 6. So these are there's 6 of them in pi over 2. So what happens is half of pi over 2 we know is pi over 4. That's great. And 2/6 of pi over 2 is pi over 6. And then 4/6 of pi over 2 is pi over 3. Now, what about these angles here? Well, another way to think of this is if I go all the way to pi over here, this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are in 12. So this would be pi over 12, and I should have started out that way. 2 pi over 12, which makes it pi over 6, pi over 4, pi over 3, and this would be 5 pi over 12 up here at the top. Okay? And I know that's small, but I wanted to do a bunch of examples on this video. So here we go. All right, so what we're going to do now is we are going to plot our polar point. Now remembering that this is in r comma theta. Okay, now what we're going to do is we're going to go out radially 3. So each one of these rings is a radius of 1. Okay, so this would be 1, 2, 3. So I go out radially 3. So here's 3. And this is the positive r polar axis here. And this is the negative r polar axis. So we're going to go out positively radially 3. And they're going to rotate to 5 pi over 6. All right, so if I do that, well, I know that this one is pi over 6, this angle. So I know 5 pi over 6 has to be here. 1, 2, 3. So I rotate radially on the 3 radius to 5 pi over 6. And I get my point here. And I'm going to label that with my handy dandy color here. This is P. Now, with polar points, I can name this point. You know, in the XY plane, it's just, if I'm over here, this is like negative 3, 1. That's the only name for this point that's possible. But in polar coordinates, I went out radially 3, and I rotated to 5 pi over 6. But I could have named this point other names. So other point representations. So P could also be, what if I rotated out positively 3 and then rotated the other direction? Well, this would be 3, and I rotate to not 5 pi over 6, but I rotate to 7 pi over 6. So this would be 3 comma 7 pi over 6, but it has to be negative because I have rotated clockwise. All right, well, what about another point? I could have gone out radially in the negative r direction. So 1, 2, 3. So I could go to negative 3, and then I could rotate counterclockwise, which would be positive. So I would rotate all the way around here, and I would get 11 pi over 6. So if when I went out radially 3 and I rotated counterclockwise, I went all the way around, and that's 11 pi over 6. And yes, I could have rotated 2, 3 out radially -3, rotated in this direction, and that would be -3, -pi over 6. So this point has, in the first go round, 4 different representations in polar coordinates. Okay. Now, of course, we could go around infinitely many times, so we have infinitely many point representations for this point in space using polar coordinates. All right, let's try another one. All right, so the next one is Q, point Q. And we're going to go out radially 4 and rotate in a positive 11 pi over 6. So we're going to go out radially 4, 1, 2, 3, 4. This is 4. And then I'm going to rotate 11 pi over 6, remembering that the second one is the 6th. Okay, so if we rotate 11 pi over 6 on this radius here, we're going to get to right here. And here again, there's Q. All right, now what are my other point representations? I'd like you to pause the tape, the video, and you do it, and then check your answers with mine. Oh, welcome back. All right, here we go. So Q could also be represented by, if I go out radially 4 and I go clockwise, negative pi over 6. And then I could also go out negatively, 1, 2, 3, 4, and then rotate counterclockwise, 5 pi over 6. That's a negative here, I'm sorry. And then I could go out negatively again, 1, 2, 3, 4, and then rotate clockwise, and that would be, I'm sorry, that's negative, 7 pi over 6, negative. And so that's 4 times. Now remember, we're doing our point, other point representations between 0 and 2 pi. Okay. All right. Now we're going to do R. Aren't you ready to do R? All right, here we go. So now this point is R theta, and I'm going to go out radially -5. 1, 2, 3, 4, 5. So this is -5. And I'm going to rotate pi over 4. That means I have to rotate counterclockwise, which means I'm going to go down here. So this would be halfway, which means I'm right here. Okay, so this is R. And let's do our other point representations. You can pause the video and you try it and then check your answer with me. All right, well, I could go out radially -5 and then rotate, oops, 1, 2, 3, 4. I put it on the 4 line. I can hear it from the background. Mrs. Muller, wait, you put it on the wrong line. You're right. All right. So I could go out radially -5, and then instead of rotating a positive pi over 4, I could rotate clockwise and have this be, well, this would be pi over 4, negative pi over 4, negative 3 pi over 4, negative 5 pi over 4, so -7 pi over 4. And then I could rotate out positively 5, 3, 4, 5, make sure I'm on the right spec. And I could rotate counterclockwise, which is positive, and that would be pi over, I'm sorry, this is clockwise. Let's go positive first. So we could rotate counterclockwise. So this would be positive pi over 4, 3 pi over 4, 5 pi over 4. So that would be 5 pi over 4. And then I could rotate out positively 5 again. 1, 2, go out radially 5. 1, 2, 3, 4, 5. And then do counterclockwise, which would be negative. So that would be -3 pi over 4. So again, in the interval 0 to 2 pi, I have 4 representations for R. S. All right, well, S is -3 pi over 2. So I'm going to go out radially -3, 1, 2, 3 on the polar axis and rotate -3 pi over 2, which means I'm rotating clockwise. So that means I'm going to be -3, and then clockwise puts me over here. So 1, 2, I'm on this ring right here. Promise to get the ring right this time, right? This is S. All right, so let's do our other representations. If I rotate out -3, and I wanted to go in the positive direction, that would mean counterclockwise. So I would go down, and this would just be pi over 2. And then I could go out radially 3 in the positive direction, 1, 2, 3, and then in the positive rotation, that would just be a positive 3 pi over 2. And then I could rotate, go out radially 3, and then rotate in the counterclockwise, which would be negative, and then so this would be 3 negative pi over 2. All right, so 4 representations. Last one here. 3, 6. You know I had to throw one that was more interesting in there, right? Well, remembering still, this is r comma theta, so I'm going to go out radially 3. 1, 2, 3, and then I'm going to rotate 6. Now remember, this is in radians. Now we could have this in degrees, but radians is my measurement of choice for right now. And if we were in degrees, this would be 15, 30, 45, 60, and so on. So, okay, so 3. I go out radially 3, but 6 radians. Now remembering that this is 0 radians, and this would be 3.14 radians. This would be 6.28 approximately radians. And it's helpful to know also that pi over 12 is about, if you were to do it on your calculator, let's pull my calculator out here. Second pi divided by 12, I get about 0.261 radians. Okay, so if I'm going to rotate 6 radians, I'm going to go just beyond, because it's 6.28, right? So if I went 6.28 minus my 0.261799, what do we get? We get 6.018, which is close. So I'm almost right on the pi over 12 line. So I'm going to go out radially 1, 2, 3, and rotate 6.0, which is about right here to the 12th line almost, but a little bit beyond. Okay, but there we go. There's T. Yeah, we can have some weird numbers, can't we? All right, so what would my other representations be? Well, it would be 3, comma, if I go out positively, 1, 2, 3 on the radially on the polar axis. And then if I go counterclockwise now, what is this angle? Well, that's -0.28, right? Because all the way around is 6.28. And if I don't go all the way around and I just need to know what that difference is, that's 0.28. All right, let's go out radially in the negative direction. 1, 2, 3. Well, if I'm going to rotate in the positive direction, it's almost as if I'm going pi, but how short? Well, that would be pi minus 0.28, which turns out to be, right, and this is T. T would be -3, comma, and if we did that on the calculator, second pi minus, whoop, I put times, minus 0.28. We get 2.86 radians approximately. All right, so what is our other measurement going to be? If I go out radially -3. Well, if I go out radially -3, 1, 2, 3, and I want to rotate the other direction, it would be pi, well, negative, right? Pi plus 0.28, right? So, because I'm going clockwise, it has to be a negative number, so I put a negative out in front of here. Okay, so it would be parentheses negative, whoops, clear, negative parentheses second pi plus 0.28 roughly. And we get negative 3.42 approximately. All right, so there are representations. A little bit more challenging. But let's say I wanted to represent this point for all angles theta, and that's what the symbol means, for all theta. If I go out positively 3 radially, how would I hit this point every time? Well, I would say it's 6 plus 2 pi n, an element of the integer set, right? That's how we would do it. And we could do the same thing with the negative. And in your homework, you're going to have to show me how to hit it more than once. Okay, so that's how you plot some polar coordinates, polar points. Well, what's really cool is that we are now going to tie together polars and the rectangular coordinate plane. And I jokingly like to call what we're going to do today the pillars of polars. We're going to use the pillars of polars. Okay, so here we go. I'm going to tie the rectangular coordinate system. So this would be x comma y with r and theta. So if this is x comma y, and I'm on some circle here, right? We would go out radially. This would be r. So what would this point be in our trig notation? Our point would be r cosine theta, right? R sine theta. And this would be theta here, our angle of rotation. And we remember, right? I know you do because you're smart folks, that this x here turned out to be r cosine theta. And this y here is r sine theta. So that's going to give us our first two pillars or polars. Now, what do I mean by that? I like to, have some alliteration so we can have some fun. Oh, because math is fun. We like to do that. I'm trying to find a different color here. Oh, well, black it is. So I'm going to turn my paper this direction. So the first pillar is, well, we know that x is equal to r cosine theta. We know that already. And then the second pillar is y equals r sine theta. Right? Because we're going to enter the building. We're going to call this building polars. And in this building, we have four pillars or columns. But pillars sounds more fun because it's a alliteration there, to use an English phrase. Okay, well, I can translate my problems if I know what x is and y is, but I need to know what r is. That's the very first expression, right? Well, r here, okay, so r equals cosine theta, y equals r sine theta. Well, what is r? Well, r is the distance from the origin or the pole outward to your point. And I can just use good old-fashioned Pythagoras and say that x squared plus y squared equals r squared. So r is equal to x squared plus y squared. Okay? So that's the third pillar of polar. So that's r equals the square root of x squared plus y squared. All right? And then the last one is the tangent of your angle theta is equal to y over x. And I'm going to put a little asterisk here. You got to watch out for your quadrant. Because you might be solving for alpha instead of theta. Okay, so tangent of theta is equal to y over x. Okay, so those are the four pillars of polars. That means if you know these equations, you can translate any rectangular coordinate into a polar coordinate. Okay, 1, 2, 3, 4 pillars or polars. And x equals r cosine theta, y equals r sine theta, r equals the square root of x squared plus y squared, and tangent of theta equals y over x. All right, so we're going to keep this in our mind. Okay? Here we go. What are our four pillars of polars again? For reference, x equals r cosine theta, y equals r sine theta, r equals the square root of x squared plus y squared, and tangent of theta is equal to y over x. All right, so these are the kind of problems that we're going to have. We're going to say we're going to convert the polar coordinate into a rectangular point, which means I'm given that this is r, this helps me to do this, r comma theta is going to go into an xy coordinate. All right. Well, I think oftentimes it's easier to go from polars to rectangular because you're given r and theta. And you know that x with our pillars of polars is equal to r cosine theta, r sine theta. All right. So what can we do? We know that this rectangular point is going to be r cosine theta, which is 2 times the cosine of pi, because they give you the angle, 2 times the sine of pi. And that turns out to be negative 2 comma 0, because the cosine of pi, if we recall, pi is over here, that point is negative 1, 0. I knew you guys knew that. Okay, so our rectangular point then would be negative 2, 0. All right, what about this one? This is remembering that this is r comma theta, and we're going to xy. So the rectangular point is going to be negative root 3 times the cosine of pi over 6, negative root 3 times the sine of pi over 6. All right, so the cosine of pi over 6 is root 3 over 2, so this would be negative root 3 times root 3 over 2, and then negative root 3 times the sine of pi over 6, which is 1/2. And so we get the point negative 3/2, negative root 3 over 2. Easy to go from polar to rectangular because of the pillars of polars. All right. Last thing, we're going to go from rectangular to polar coordinates. All right, so we're going to review the pillars of polars. What are the pillars of polars? Oh, wait, x equals r cosine theta, y equals r sine theta, r equals the square root of x squared plus y squared, and theta equals, tangent theta equals y over x. Okay, so now what are we going to do? We're going to take and we're going to convert from rectangular to polar. So what we have here are x comma y's, and we're going to change them to r comma theta. Okay, well, what I like to do is to plot, when I go this direction, it helps me to know what quadrant I'm in. So here we go, I'm going to graph this point. This is going to be negative 1, 1. So I'm up here. Okay, so I need to know what the distance is from the pole to my point, which is this distance, right? So the first thing I'm going to calculate is r. Well, r is just simply the square root of negative 1 squared plus 1 squared, which is equal to the square root of 2. So I know r is root 2. That's my first point, or my first coordinate. Now I need theta. Now, if I go out radially, root 2, I'm going to do the positive angle here, okay? So I got to find out what theta is. So I know the tangent of theta is equal to the y over the x, which is 1 over negative 1. So tangent of theta equals negative 1. Well, what quadrants is the tangent negative? Well, the tangent is negative in quadrants 2 and 4. So alpha is equal to pi over 4, but I need this angle here. So that theta is going to be 3 pi over 4. Okay. Now, this is my point, but that's only one of them. I could have also said root 2, and if I wanted the negative angle, it would have been rotating from the polar axis out radially, root 2, and then to negative 5 pi over 4. I could have done that because this would be pi over 4, 3 pi over 4, 5 pi over 4. And then I could have done the negative rotation. So I could say negative root 2 radially, and then rotating counterclockwise or clockwise, it would be negative pi over 4. And then I could have done negative root 2 and rotated counterclockwise, and that would be negative or positive 7 pi over 4, sorry. All right, 0, 2. 0, 2 means I'm going up here. Well, in this case, r is pretty simple, right? Because we can see clearly that r is equal to the square root of 0 squared plus 2 squared, which is just 2. So my polar point is really simply 2, and I need this angle theta here, pi over 2. And I could do radially out 2 and rotate in the negative direction, so that would be negative 3 pi over 2. I could also say negative 2 rotating out, going out radially negative 2 and rotating counterclockwise would be 3 pi over 2. And then negative 2, if I went out radially negative 2 and then rotated clockwise, that would be negative pi over 2. So these are the 4 representations between 0 and 2 pi that I could have done for that. All right, well, let's do a more challenging point that I know that's not on here, okay? One that we might need our calculator for. So I want somebody to yell out a problem or a XY coordinate. And let's be in quadrant 3. Ah, yeah, I heard from the corner over there. Mr. Turner said negative 2, negative 7. Now that's a pretty point. But what's our first step? Remembering that this is an x and a y, and we're going to go to an r and a theta. Well, the first thing we got to find is r. Well, r is simply the square root of negative 2 squared plus negative 7 squared, which is the square root of 4 plus 49, which is a beautiful root 53. Okay, but then I need to find the theta. Well, tangent of theta is equal to y over x, which turns out to be negative 7 over negative 2, which is 7 over 2. But if I'm going to plot this point, right, negative 2, negative 7, I'm down here, right? So I need this angle. So I got to find alpha. Alpha is inverse tangent of 7 over 2, and I have no idea what that angle is. And I am in radians. So how do I do that? We're going to go second inverse tangent of 7 divided by 2. And that's going to give us alpha is 1.29 radians, roughly. Okay, and if I want the angle for my point here, if this is alpha, I got to find theta. So theta is going to be, since I'm in quadrant 3, pi plus, right? So second, pi plus, and I'm going to say the answer here, and we get 4.43. So my first polar representation would be, I'm going out radially, root 53, again, a beautiful number, and I'm going to rotate in the counterclockwise direction, 4.43 radians. Or we could say I'm going to rotate out negatively, root 53. Go out radially, negative root 53. And if I rotate in the counterclockwise, right, direction, that would be a positive angle, and then I could use my alpha, so that would be 1.29. And then what are my other points? I could have a positive root 53, and then if I rotate the other direction, it would be pi minus alpha. So second pi minus, go grab my alpha up here, and that's going to be negative 1.43 roughly, because I went in the clockwise direction, and then negative root 53 if I go the other direction. So I rotate out negatively, not rotate out, go out radially negative 53, and then I go clockwise, that's going to be 2 pi minus alpha. And that's negative 6.15. Okay, so just practice some of this, and we will chat with you next time. Have a great rest of your day, and have some fun converting from rectangular to polar. Oh, and the other thing is that why do we do this? I put Desmos up here. I'm going to go over to the little arrow here, or the graph settings, and I'm going to change this. I want you to notice, please, that this right here is a grid. I can put polar coordinates on here. Look at that. Wow. And I'm in radians, so you can see that it has the nice radians here. Okay, so you can plot some polar points here if you want, I think. I wonder what happens if we just do one point here. Let's say we do square root 2 comma pi over 6. Look at that, it plots our point. So it does an r theta for you, which is really cool. Now, why do we do polar coordinates in the first place? Well, some equations are easier to write in polar form than they are in rectangular form. I'll give you an example. Let's try x squared plus y squared, and I'm foreshadowing what we're going to do next time, equals 1, right? That's our favorite unit circle. Everybody agree? Yeah, well, of course it is. All right, well, what is r equal? R equals the square root of x squared plus y squared, right? So I can just say r equals 1, and look at that. In polar form, a circle is r equals 1, which is a much easier equation than x squared plus y squared equals 1, because there aren't any squares, and it's a really simple equation. Well, what about equations of lines? Well, y equals x. Here it is. There's y equals x. That's an equation of a line. Whoop. I was trying to hide these for a sec. It's the equation of a line. Well, in polars, well, what r is, it doesn't matter what r is. I have only one theta, so I can type in theta equals, well, what is the angle always? The angle's always pi over 4. No, it doesn't like that, does it? I don't think we can graph it that way. But anyway, the equation of this line would be theta equals pi over 4 for all time, which is pretty cool. Anyway, that foreshadows what we're going to do next time. But anyway, have a great day, and we will chat with you later. Thanks. Bye.